everyone, Mrs. Hanson here again, picking up with your Chapter 8 lessons. We're in Chapter 8, Section 7. We're going to talk about diluting a solution. So we'll define dilution, and just think about it. You want to dilute a solution and pour more water in it, aren't you? Dilution is the addition of a solvent to decrease the concentration of the solute. So keep in mind our molarity formula, where we define that concentration unit, big M, capital M, for molarity, as moles of solute per liter of solution. When we add more solvent, we're creating a larger volume, but we really have not changed the moles of the system. In other words, let's think about Kool-Aid, I don't know, lemonade, something where you pour a powdered mix and stir it up into water and you get a solution. If you've ever made Country Time lemonade or Kool-Aid, you're going to pour in a packet of powder into a quantity of water, stir it up, and let's suppose it's too strong, it's too concentrated. To dilute that, you simply add more water, don't you? What you've not changed is the amount of solute. Right, the amount of Kool-Aid or lemonade going into that solution has not changed. That was constant. However, what did change was this amount of volume of the entire solution. So if this is constant, moles is constant, and we know that moles can be defined as molarity times volume in a liter, we can actually calculate the new concentration of our diluted solution with this formula right here presented. The initial molarity and volume of the solution will be equal to the new concentration and new volume final values, MV equal MV. You dilute the solution by still making the same quantity of moles. And that's why this equation works. The moles was constant. I did not change the amount of solute provided, but what I did change was the volume. So if the volume went up, of course the molarity went down. They were inversely related. So when we want to find a new concentration, we use a formula, MV equal MV, where the initial molarity and volume is set equal to the final molarity and volume. Shall we try one? What is the concentration of a solution formed by diluting 5 mils of a 3.2 molar solution? Here I'm reading that molar for big M, just to kind of hear how I'm reading that. And we're looking for the new concentrations when V2 has been changed to 40 mils. What is the new concentration? So we know our formula, M1V1 will be equal to M2V2. 3.2 molar times 5.0 mil, that's M1V1, set equal to our target variable, M2, times 40 mils. Now to pull out M2, we're going to multiply 3.2 and 5 and set that over 40. And then we solve for that, we'll get our new molarity. You know it's going to be a number smaller than 3.2 because we diluted it. We made it less concentrated. 3.2 times 5 divided by 40. And my calculator reads 0.4. We're going to need 2 sig figs, so 0.40, and my unit there is big M, and remember when you read that, it stands for molar units. Not too bad, right? Let's try another together. What is the concentration of a solution formed by diluting 25 mils? Can you hear my Roomba in the background? I'm vacuuming. And the first molarity is 3.8 molar. We're going to dilute that to a total volume of 275 mils. What's the new concentration going to be? So we're adding more water, diluting the solution. So M1V1 equal M2V2. Our first set of conditions set equal to the second set of conditions. Remember to isolate M2 we're going to take 3.8 times 25, divide by 275, and you'll solve for M2. 3.8 times 25 divided by 275 equals, and my screen reads 0.34545 repeating. Looks like we need 2 sig figs, so I'm going to report that as 0.35 molar. And that capital M is the abbreviation, but we read that by saying molar. Excellent. Dopamine is a potent drug administered intravenously to increase blood pressure in seriously ill patients. How many milliliters of a 4% weight by volume, oops, I should put a percent in there, must be used to prepare 250 mils of a 0.08% weight by volume. So you know what, instead of molarity, we were given a different concentration unit. Whoops, I can spell. I'm sorry. Let me erase that and make that correct. Instead of molarity, we were given percent weight by volume. But that is not anything to worry about, because our formula can really be written as whatever the concentration unit is times the first volume will give us the new concentration unit and the second volume. So whatever the concentration is that you put in will be the same concentration unit you get out. They will match, and that's what algebra does, is just match units. So if our first concentration unit was 4%, we'd like to know the volume, so that's our first volume variable. The second condition was 0.8%, and that volume was 250 mils. So we had a concentration unit, volume unit, set equal to a new set of conditions. We want to pull out the first volume. So all we're saying is whatever that concentration unit, if it's molarity in, you'll get molarity out. If it's a percent that you put in, you'll get the same unit back. So V1 can be solved for by taking 0.08 times 250 over 4. And let's solve for that and see what we find. Whoops, I have to clear screen. 0.08% times that volume of 250 divided by 4%, and the unit here is 5, or the number that comes out on my screen is 5. We will need 2 sig figs, so I'm going to put 5.0, and remember the unit we put in will be the unit we get out, so this will come out to us as 5 milliliters. Easy peasy. Why don't you try some? Calculate the volume in milliliters of a 6 molar NaOH used to prepare each solution. Pause your video and try these out with your calculator. Remember, I'm looking for you to show your work in your notepad to earn full credit. Pause, think, and come back. Welcome back. In letter A, you had 525 milliliters of a 2.5 molar solution. I'll call these the initial conditions, M1, V1. The stock solution was a 6 molar NaOH solution. How much are we supposed to take out of that in terms of volume to dilute up to 525 mils? So you can think about how many mils needed in terms of MV equal MV. V2 comes out here by hitting 525 mils times 2.5 molar over 6 molar equals. And you know that this algebra does not matter. If I had put 2.5 first, 525 first, or second, doesn't matter. You're going to get the same answer, aren't we? 525 times 2.5 divided by 6. And my screen reads 218.75. Let's think about sig figs. We're given 3 units here in the volume, but only 2 in the molarity. So I'm going to say that's 220 mils for sig figs, and I will not put a decimal, so that remains as 2 sig figs. Here's letter B. We had 750 mLs times 4 molar, and you're simply setting that equal to 6 molar and solving for V2. On your calculator, you hit 750 multiplied by 4 and divided by 6. And that came out to be 500 mLs. Letter C. 450 times 0.1 molar set equal to 6 molar times V2. So on your calculator, you hit 450 times 0.1 divided by 6. And this came out to be 7.5. So what is that, a ml? And I can squeeze in, how about letter D if I put that up here? Here's a letter D for us, 25 mils times your 3.5 molar set equal to 6 molar times V2. My calculator will go 25 times 3.5 divided by 6. My screen reads 14.583. Let's consider 2 sig figs, so I better round up, 15 mils. Easy peasy. We just performed dilution problems. The concentration and volume of your first set of conditions set equal to the concentration and volume of the second set of conditions. If you're using molarity, that might be a more familiar reaction, MV equal MV. In our next section, we look at some physical properties that change of a solvent when we add a solute, when we create a solution. These are physical properties that change. Let's define the term colligative property. These are the physical properties of a solution that depend upon the concentration of the solute, but not its identity. It doesn't matter what you put in, just how much. A colligative property are physical properties such as boiling point, freezing point, and osmotic pressure. These properties of a solution depend upon the concentration of the solute, but not its identity. In my own words, it says, if I want to make a solution, it doesn't matter really what I pour in. I could pour in salt, sugar, whatever it might be, but it's the amount of solute I pour in that changes the boiling point or freezing point based on that amount. The number of dissolved solute particles affects the properties of the solution, but not the identity. And colligative properties include the elevation of boiling point. So boiling points increase. Pure water would boil at 100 degrees Celsius. Salt water or sugar water or a solution is going to boil higher. Freezing points actually decrease, they depress, they go down. Pure water freezes at 0 degrees Celsius. Solutions are going to freeze below 0 degrees Celsius. So if we think about the liquid phase of water, and over here it would be solid, and over here would be gas, or which we would call steam. We would know at this particular temperature, 0 degrees Celsius, we have a phase change. And 100 degrees Celsius, we would have a phase change from liquid to gas. What colligative properties say is if this is pure water and we had a solution of water, we actually extend the liquid phase. So that if this represents a solution of water, and this, the first graph I wrote down was pure water. Water in a pure form would have a 0 degrees Celsius freezing point and a boiling point of 100 degrees Celsius. If I make a solution of water, so say salt water or sugar water, it would have a freezing point below 0 degrees. And it would have a boiling point above 100 degrees. We've extended the liquid phase by just adding a solute into the solvent. And let's explore this a little further. The boiling point elevation is defined as the liquid solution that contains a solute. It will have a higher boiling point than the solvent alone. And the amount that the boiling point increases only depends upon the number of dissolved particles. It depends upon how much, but not the identity. So if you have more and more and more salt in the water, you're going to change the boiling point even more, and you'll change the freezing point even more. I wanted to just take a moment and remind you about electrolytes, which are these soluble salts in water. And do you remember the term non-electrolytes? These are soluble molecules in water. Because these soluble salts dissociate, they separate, they give us more particles as they form ions. And we have to count the number of ions when we're looking at the effect on the boiling point. These molecules do not dissociate, do not form ions, do not separate, and stay as just one particle. When I say molecules, I want you to think of those nonmetals that are covalently bonded together, like sugar, C6H12O6. We said that this is a non-electrolyte. It does not separate into ions. Whereas if an electrolyte, let's say sodium chloride, is a water-soluble salt, we know that it is a metal with a nonmetal, that it's built of ions, and that we practiced recognizing that 2 aqueous ions would come out. Remember how we said ions are always aqueous? So you get 2 ions that separate out when you put sodium chloride into water. So the number of particles has to be accounted for by considering electrolytes versus non-electrolytes in solution. Electrolytes affect the change in boiling point more than non-electrolytes because they dissociate. What that means, remember, is that they separate into ions. How many particles? Well, let's practice. How many particles are in the following? To do this skill, step 1, ask yourself, is it ionic or molecular? And if you answer ionic, that's because you see a metal ion electrically balanced with a nonmetal ion. And if you answer molecular compounds, these are all nonmetals that are covalently bonded, not built of ions at all. So when we practice that, KCl, for example, KCl is a metal. It's on the left side of the periodic table. Chloride is a nonmetal. It's on the right side of the periodic table. That when KCl is an ionic compound, When it's placed into water, it separates into aqueous ions. You get a potassium ion and a chloride ion. This gives us a total of 2 ions in solution. Let's try number 2, magnesium chloride. Magnesium is a metal. It lives in group 2A on the periodic table. Chloride is a nonmetal. It resides on the right side of the periodic table. When magnesium chloride dissociates in water, it forms aqueous ions. The magnitude of the charge on magnesium is a +2. That's why I can see it needs 2 chloride ions to balance that electrical charge. Remember the visual? If magnesium is a +2 and chloride is a -1, we need 2 chlorides to electrically balance the magnesium. How many total ions are there? Well, there's 3. 1 magnesium and 2 chlorides for a total of 3 ions. Number 3, carbon, hydrogen, oxygen. This is a molecular compound. And molecular compounds do not dissociate. So we have just one particle. The molecule itself retains its identity. Here we have potassium nitrate. Hear that polyatomic sound? The polyatomic ion known as nitrate. Potassium nitrate is an ionic compound. We have a metal hooked to nonmetals in a polyatomic ion charge. When potassium nitrate is placed into water, the potassium ion separates from the polyatomic ion nitrate. Remember the nitrate, this is one unit. A polyatomic ion stays together. It does not dissociate away from each other, but acts as a unit carrying a charge. So you have 2 ions total. Now we're practicing that because when we're asked to calculate the change in temperature, we have to account for all the possible number of particles in solution. 1 mole of a solute raises the boiling point of 1 kilogram of water by 0.51 Celsius degree. This is called the molal boiling point constant. Just so you can hear what that constant means, that the change in the boiling point, and we can write this together, the change in the boiling point is going to be equal to the moles of solute per kilogram of water times our molal constant times the number of particles. The concentration unit, which here is known as, we can go ahead and define it. This is a little term called molality. It's a little different than molarity because we have kilogram instead of liter underneath here. This is the constant for water, 0.51 degrees Celsius. And this is the number of particles that dissociate. And I'll go ahead and tell you the name of it. It's called the Van Hoff factor. That's a person's name. Let's give you an example of how this would work. What is the boiling point of a solution? All right, so here I'm looking for the change in the boiling point that contains 0.45 moles of the solute KCl in a kilogram of water. We know that the constant says for every 1 mole in a kilogram of water, the boiling point is going to raise by 0.51 degrees Celsius. Then we have to consider how many particles come out when potassium chloride is placed into water. So the solute here is potassium chloride. How many particles? First of all, recognize that it's ionic. It's a metal with a nonmetal. And when potassium chloride is placed into water, aqueous ions of potassium and aqueous ions of chloride dissociate. That gives me a total of 2 ions. And that's my strategy to find the change in the boiling point. I can find the change in the boiling point by finding the concentration unit, which is 0.45 moles for every kilogram. So I'm going to, in my calculator, hit 0.45. I'll multiply that by the boiling point constant for water, 0.51, times 2. By the way, you do not need to memorize 0.51. It will be given to you in the story problems. So 0.51 is the constant. I say that, I'm almost sure. Let me just get back to you on that. When I read the story problems, they were always provided, but 0.51 is the constant. Put yourself, if it were me, I would say this in my highlighter. I'm going to just make that highlighted in my notes so I can find it. 0.51, the boiling point constant for water. So if I'm reading a story problem just like this, and it's not given to me, I have a reference to go back and remember it. Did I ever hit equal? Nope. When I hit equal, I found 0.459. Okay, so what does that mean? Remember, this means change, the change in the boiling point. We know that water normally boils at 100 degrees. But I also know that a solution is going to elevate the boiling point by 0.459 degrees. So what is the new boiling point? Well, the new boiling point is going to be 100.459 degrees Celsius. It's a little bit higher than the pure water. And I would say that's plenty of decimals there, isn't it? Don't round it so much that you just say 100, because you need to see the difference. It's elevated to 100 point, let's say 2 decimals, just to be sure you see that it increased, raised up a little bit higher by forming a solution. Alrighty, let's take a peek at another set of practices. We're going to take the boiling point of a solution from each of the following solutes dissolved into a kilogram of water. Remember our formula. The change in the boiling point is equal to the concentration unit, which is moles of solute per kilogram of water. That's the concentration unit, times our boiling point constant, 0.51 degrees Celsius, times the number of particles. Now notice this did not give us the 0.51, so I had to know that to do this practice problem. So this part right here I had to remember. So let's take a letter A for example. The change in the boiling point will be found by taking the concentration, which is 2 moles of sucrose in a kilogram of water, times the boiling point constant for water, times the number of particles. Well, how many particles in sucrose molecules? That's a big clue, isn't it? Sucrose, even if you didn't know its chemical formula by heart, it gave you a big clue right here. Molecules do not dissociate. Molecules are made of nonmetals covalently bonded. So the number of particles for any molecule is simply 1. They do not separate. So the change is going to be equal to 2 moles divided by 1. So just simply 2 times 0.51. Whoops, I hit a wrong button. 2 times 0.51. And my screen reads 1.02 degrees Celsius. And remember, that's the change in the boiling point. We want to know the new boiling point. Water normally boils at 100 degrees. it's now raised by 1.02 degrees Celsius. So the new boiling point, 101.02 degrees Celsius. I'm going to leave those decimals there so you can see that these are small changes, but nonetheless, they will raise the temperature of boiling. Letter B, the change in the boiling point is set equal to the concentration of the solution. Here we have 2 moles of potassium nitrate in a kilogram of water. The boiling point constant for water is 0.51 degrees Celsius. And now, how many particles in potassium nitrate? Well, recognize this is called a salt. It's an ionic compound. An aqueous ion of potassium and an aqueous ion of nitrate gives us a total of 2 ions. So we have 2 particles in solution, the potassium ion and the nitrate ion. So the same quantity of sugar and this salt, the salt is going to have twice the effect because it can dissociate and give me twice the number of particles. 2 times 0.51 times 2 gives me 2.04. That's the change. So remember, the new boiling point would be added to the original 100 degrees. And now it's going to boil at 102.04 degrees Celsius. A slight change, a little bit of an elevation. How about letter C? Oops, jumped the screen. Let me go back up. Here's letter C. 2 moles of calcium chloride. So my change of boiling point is going to be equal to, trying to get rid of that. There we go. Change of boiling point, we have 2 moles of calcium chloride in a kilogram of water. For every 1 molal, it's going to raise by 0.51 degrees Celsius. That's the freezing or the boiling point constant for water. How many particles in calcium chloride? When calcium chloride dissociates, we get 1 aqueous ion of calcium and 2 aqueous ions of chloride. Remember this visual. Calcium with its magnitude of charge is +2. Is going to require 2 chlorides to balance it electrically, because it's only a -1. That gives us a total of 3 particles. 2 times 0.51 times 3. And this gives us a boiling point change of 3.06 degrees Celsius. So the new boiling point is 100 degrees, the normal for pure water. It's going to elevate by 3.06 degrees, so the new boiling point is 103.06 degrees Celsius. And letter D, 20 grams of sodium chloride. I just wanted to rewrite that. All right, so this is a little different in the sense they're making me do a little mole map problem, aren't they? Remember your round little buddy for moles? Grams over molar mass is a mole. That's just an old mole map problem. So I need to do a little molar mass work. Let's see, sodium is 23, chlorine is 35.5. It might be 4 or 5, but I'll just round for that decimal. And that gives me 58.5 as the molar mass. I have 20 grams and the molar mass of 58.5. So I'll just hit that for us. 20 grams divided by 58.5. That's 0.3418. Let's say 0.342. And now we have what we need to set up our change in the boiling point formula. So the change in the boiling point can be found by taking the moles of salt, and that's in a kilogram of solution, times the boiling point constant, 0.51 degrees Celsius, times the number of particles. Well, the sodium chloride is built of two ions, a sodium and a chloride. When it dissociates, we get two aqueous ions. One of the two is sodium. The second of the two is the chloride. I have my moles on my calculator already, so times 0.51 times 2. And this series gives me 0.3487, so I'll say 0.35 is the change in the boiling point. So water normally boils at 100. It's now going to elevate by 0.35 degrees. So the new boiling point is 100.35 degrees Celsius. Just a slight elevation in that last one. Okay, let's take a peek at freezing points. Now, freezing points depress. That means they lower. So a liquid solution that contains a non-volatile solute has a lower freezing point than the solvent alone. So salt water freezes lower than a pure solution of water. That's why we put salt on the roads in the wintertime to melt the ice. The amount of freezing point depression depends only on the number of dissolved particles, not the identity, but the number of particles. You're going to see a very similar formula as we were working with boiling points, but we have a different constant. So here's the constant, and I would highly recommend taking your highlighter and make sure you can find that 1.86. Remember that number for these problems. So for every 1 mole of solute in a kilogram of water, the freezing point depresses by 1.86 degrees Celsius. So our formula, very similar. The change in the freezing point will be found by taking the moles of the solute per kilogram of water, that's our concentration unit, times the freezing point constant, 1.86 degrees Celsius, times the number of particles. So this is exactly the same formula as boiling point, except we have a different constant. Every 1 mole of a solute is going to lower the freezing point by 1.86 degrees. So you can see that we have a greater effect on freezing point than boiling points. Let's try one out. What is the melting point of a solution that contains 3 moles of calcium chloride? So there's our moles, 3 moles of CaCl2, that's rock salt. And we're going to put that into a kilogram of water. We know that our boiling or freezing point constant, 1.86 degrees Celsius. This calcium chloride is used as rock salt to melt ice and snow on the highways and sidewalks in the winter. For every 3 moles of rock salt we put into a kilogram of water, what will the new freezing point, melting point, what will it be? Well, how many particles are contained in calcium chloride? Can you see that? Calcium chloride is built of 3 ions. You get 1 aqueous ion. Remember, ions are always aqueous. And you get 2 aqueous ions of the negative. So that's a total of 3 ions. Just another visual for us. Calcium's magnitude of charge is +2. It's going to take 2 units of the -1 chloride to electrically balance the +2 calcium. So that's a total of 3 ions. That's why we use rock salt instead of sodium chloride, which only contains 2 ions. We're going to affect the freezing point more with calcium chloride and its 3 particles. So 3 over 1 times 1.86 times 3. Oops, I hit the error. Darn it, I have to hit that again. Sorry, clear screen. 3 over 1 times 1.86 times 3. Now I've got it. My screen reads 16.74 degrees Celsius. Now remember, that's the change in the freezing point. Water normally freezes at 0 degrees Celsius. That's its normal freezing point. It's going to depress, which means to lower, by 16.74 degrees Celsius. You lower the freezing point, so you subtract. So the new freezing point is now going to be negative 0.6. Oops, let me make that more clear. The new freezing point is going to be equal to negative 16.74 degrees Celsius. That means it can get to negative 16.7 degrees outside and we'll still have liquid instead of solid on the roads. We're lowering the freezing point. Let's try some of these. These look exactly the same as the previous slide. Oh, except now we're going to melt instead of boil. All right. So letter A, do you remember how we stressed letter A? This was a molecule. Even if we didn't know the formula for sucrose, which we do, C12, H22, O11, the key here is molecules. They do not dissociate. So that's simply one particle. So when I think about letter A, I have 2 moles of my solute, my change in freezing point, is going to be equal to the 2 moles of sucrose in a kilogram of water times the freezing point depression constant, 1.86, times the number of particles. The number of particles here is 1. Let me pause this. I just got a message I need to answer. Hang on. Okay, I'm back, ready to do a little more calculating. We were working on finding the new melting point of a solution, putting 2 moles of sugar into a kilogram of water. So I was hitting 2 times 1.86, and what that found for me was a value of 3.72 degrees Celsius. Remember, that's the change in the freezing point. Water normally boils at 0 degrees. Not boils. Water normally freezes at 0 degrees. I'm sorry. It's going to depress by 3.72 degrees. So that means it's going to lower to negative 3.72 degrees Celsius. There's your new freezing point. In letter B, our change in freezing point will be found by taking the concentration unit, 2 moles of potassium nitrate, in a kilogram of water. We know that every 1 mole would lower it by 1.86 degrees Celsius. And we remember that potassium and nitrate contains 2 ions. 2 times 1.86 times 2. The change in the freezing point comes out to be 7.44 degrees Celsius. So the new freezing point is going to be 0 minus 7.44 or negative 7.44 degrees Celsius. And in letter C, you found the change in freezing point by taking 2 moles of calcium chloride in that kilogram of water. You then multiplied it by 1.86 degrees Celsius, and you counted 3 ions in your calcium chloride solution. CaCl2 contains 3 ions. 2 times 1.86 times 3. And that is 11.16, isn't that? Is that what you got as well? 11.16. So therefore, the new freezing point would be negative 11.16 degrees Celsius. Brr, that's getting cold. And of course, letter D, this is the one where we were given grams of sodium chloride, 20 grams of NaCl. Remember how we divided that by 58.5, which was the molar mass? And when we did that, we found the moles of salt to be 0.342. And that kilogram of water times 1.86, that's my email going nuts, times 2 ions. So the change in the freezing point is 0.342 times 1.86 times 2 ions, and that's 1.27. So the new freezing point would be negative 1.27 degrees Celsius. Good work. Try this problem on your own, and I'll come back and check with you in just a moment. All right, well, welcome back. Let's see how you did. We were trying to calculate the change in the freezing point, which, remember, don't let this bother you. Freezing point, melting point is the same temperature. And so here we're given 250 grams of ethylene glycol, which is C2H6O2. We're going to need to divide that by its molar mass to convert it to a mole. So just remind yourself, the grams over molar mass is a mole. We need to add 2 carbons at 12 apiece, hydrogen with its atomic weight of 1, and there's 6 of them. Oxygen has 16 for its formula weight, and there's 2 of those in the formula. So let's sum all of the weights of these individual atoms. 12 times 2 plus 6 plus 16 times 2 gives me a total mass of 62 grams. So my molar mass goes underneath the 250 grams. And let me just divide that for us and find moles. So did you find this as well? 4.032, and I can just keep all those decimals for now, and we'll just round at the end. So again, our change in the freezing point or melting point, same thing. The number of moles per kilogram, and there's just one. There's 1 kilogram. There's our concentration unit, times the freezing point depression constant, 1.86 degrees Celsius, times the number of particles in solution. And I bet you notice that this is a molecule, right? It's all non-metals. It does not dissociate. So it's just simply 1 particle. So my 4.032 that I still have on my calculator screen times 1.86 times 1 is 7.5 degrees Celsius. Now remember, the new freezing point lowers it from 0 degrees, so it becomes negative 7.5 degrees Celsius. We have lowered the freezing point or the melting point, same temperature. Let's talk about osmosis and dialysis. You know, in your biology class, even probably from high school, middle school, you studied cellular functions. And you know that a cell membrane is one that surrounds living cells, and it's said to be semi-permeable. A semi-permeable membrane allows water and small molecules to pass across, but larger substances, large molecules or large ions, are not allowed to pass through these channels. Osmosis is the passage of a solvent, usually water, across the semi-permeable membrane from an area of low solute concentration to an area of higher solute concentration. From an area of low concentration of solute to a higher concentration of solute. Now you think about what that really is saying. A low concentration of solute means mostly water. This is dilute. And it's flowing to a higher concentration of water, which is less water, more solute, which is what we call concentrated. So an area of high water to low water is the diffusion process called osmosis, from a more dilute solution to the more concentrated solution until we have an equilibrium achieved. And you can see here we have a solute plus solvent, a semi-permeable membrane just based on the size of those particles, and on this side is the solvent only. The water is allowed to diffuse through, and the water itself is the dilute side, which is the solvent only, and it passes across this channel to the more concentrated side. Water will flow from the more dilute to the more concentrated until we have an equilibrium achieved. This osmotic pressure is defined as the pressure that prevents the flow of additional solvent into the solution on the side of the semi-permeable membrane. So on this side, this is a semi-permeable membrane separating this beaker into two components. Here we have pure water, and on this side we have sugar water. So here's your mixture. After time goes by, think about the semi-permeable membrane allows water to diffuse, not the sugar, but just the water to diffuse, and it goes from the more concentrated side. And notice how the water ended up over here. So this was what we referred to as more dilute, heading to the more concentrated side. And you actually see the water levels do indeed change. The water flowed from the pure water over to the solution side. That term, osmotic pressure, prevents the flow of additional solvent once that equilibrium is reached. Osmotic pressure is a colligative property. And let's kind of go through these points. Well, we'll go through them one at a time. So let's kind of just cover them up and discuss. This is a colligative property, which means the more solute you have in that solution, the greater the osmotic pressure. Remember, it doesn't matter the identity, it just matters how much. And the more and more and more particles you have in solution, the greater the osmotic pressure. And water always flows from the side of the less concentrated solution, which we defined as dilute, to the more concentrated solution. So dilute to concentrated is the flow of water. So think about where there's more water, the solution is dilute. Where there's less water, the solution is concentrated. And that's our flow of water across that semi-permeable membrane. Water flows from the side where there is more water to the side where there is less water. Now let's kind of think about that. We have a 0.1 molar glucose solution, and it's separated from a 0.2 molar glucose solution. So we have a beaker with a semi-permeable membrane separating two components. On one side, we have a 0.1 molar solution. On the other side is a 0.2 molar solution. Which solution exerts the greatest osmotic pressure? Osmotic pressure is a colligative property. The more and more and more particles you have in solution, the greater the osmotic pressure. Which solution exerts the greater pressure is the one with more particles. It would be the 0.2 molar side because it's more concentrated, more particles in there to exert pressure. And letter B says, in which direction will the water flow between the two solutions? Remember, water flows from the more dilute to the more concentrated. It is going to flow from the 0.1 molar to the 0.2 molar. It flows from the more dilute to the more concentrated side. Describe the level of the two solutions when equilibrium is reached. So at the start, we had an equal volume. And at the end, as water flowed, the 0.1 molar would go down and the 0.2 molar would go up. As water flowed from one side to the other until an equilibrium was achieved, we have two different water levels. Let's think about the following. Which solutions in each pair exerts a greater osmotic pressure? Osmotic pressure is a colligative property. Which tells me the more concentrated the solution, the more pressure there is. There, I just wanted to be sure to write that note for you. So we have a 1% sugar solution or a 5% sugar solution. Of course, the 5% is more concentrated and therefore would have a greater osmotic pressure. 3 molar sodium chloride or 4 molar sodium chloride, same solution. The more concentrated solution would have greater osmotic pressure. This one's a little tricky. 1 molar glucose, which is a molecular compound, so only one particle, or 0.5 or 0.75 molar sodium chloride, which actually contains 2 ions. So you'll have twice the value. So in other words, 0.75 with its 2 ions, 1 molar, would have an effect really of just 1 particle. So you'd end up with 1 molar overall. 0.75 with its 2 particles. Well, what's 0.75 doubled? That's 1.5. And therefore that is the more concentrated solution. So therefore 1.5 molar sodium chloride would have a greater osmotic pressure because you have 2 particles that come out. How'd you do? When you look at, I think I went too far, the osmotic properties in dialysis, a little focus on the human body here. And I'm going to just ask you to go into your notes, into your textbook to finish your notes here and do a little bit of reading about osmotic pressure in terms of blood cells. If we have osmotic pressure the same on both sides of a red blood cell, for instance, the solution will be isotonic. And I want you to go in and do a little reading about hypotonic. And I want you to do a little reading on hypertonic. And think about what happens when cells will, when we think about what cells do when they're placed into a solution. Another part that I'm going to ask you to do, focus on health and medicine, is the dialysis section in section 9 of chapter 8. Do a little reading here on the medical process of dialysis. And that will actually finish up your note pack through the process of a little more reading. And you did it. This is the end of chapter 8. Don't forget your assigned reading. Do some ample note taking and then submit your notes when ready.